We have already discussed about the point of zero charge, how it has to be determined experimentally, either by potentiometric titration or by zeta sizer, which gives the zeta potential determined as a function of the pH values, and from that we can find out point of zero charge of the PZC values. Now, as I've already mentioned, that depending on the pH values and the PZC of this adsorbent or the clay mineral, whatever we are talking about, so based on that, the metal ion uptake can be decided. For example, if the PZC value of a particular clay mineral is around 7, then the pH value lower than 7, that it will exist in the protonated form. So naturally, the uptake of the protonated species will not be there onto this mineral surface. But if we increase the pH value to higher than that of the PZC, then these hydrogen ions are dissociated or removed from the surface of this clay mineral, and we have the O minus or negatively charged species at the surface of this clay mineral, and then which will be now forming the complex with the cationic species if present in the aquatic system. If it is forming a complex or if it is forming anionic species, the actinide ion, then it will naturally not form complex at the pH value higher than that of the PZC. Now coming to the surface charge characteristics of these minerals, the figure shows that how you have this negatively charged in the faces you have, and also the positive charge edges are there. So they will be actually binding with the cationic as well as the anionic species. That is, the cationic species will be binding with the faces and the anionic species will be binding with the edges. Then in this case, when the presence of the variable charge surfaces as shown here, the number of surface sites are constant, but their individual charge and the total surface charge will be vary as a function of the solution composition. The surface charge depends on the absorption, surface binding of the potential determining ions, such as the hydrogen ion, and the formation of the surface complex also affect the surface charge. A mix of anion, cation, and neutral species can jar and modify the clay. Now, what are the factors which are affecting the absorption process? That is, number one, it is the surface area and the amount of absorption site. If we have a very large surface area, that is, the same mineral you are having finer particles, then it will have a very large surface area for a particular weight of the clay mineral. So in that case, the surface area has increased. So naturally, that will be also having higher uptake of the actinide ions or the metal ions, and also the amount of absorption sites, that is the density of the absorption sites in the mineral surface. As shown here, you have this bulk mineral phase which is shown here. Now, how many sites are there which are binding in the metal ion? That also is dependent on the amount of actinide or the metal ion which is taken up by the mineral phase or the bulk mineral phase. Then the relative attraction of the aqueous species to the absorption sites. There are some other species which are present in the aqueous phase which are also going to the absorption sites. Then permanent structural charge and also variable charge. These are the factors which are deciding the absorption process. Now the mechanism of this can be two-way. First is the ion exchange, which is happening in case of the clay minerals like smectites and zeolites. So in this case, we have this example given here that you have the neptunium ions are there. So the charge is not given, but you can consider suppose neptunium plus 5 state, that is neptunial ion is there. So then how it will be forming complexes with the bulk mineral phase, or it will be transporting as such. So as shown here, some of this neptunium will be forming, of course, directly it will be forming complex with the surface of this bulk mineral phase. Then it can also bind with some of the mineral colloids with these bigger size species which is shown here. This is the mineral colloids which are there. Now what is the colloid that I will be discussing subsequently in this lecture. So is this neptunium is binding to this mineral colloid which is there, and this also can move. There is a transport of this can be there. Neptunium can, as such, it can be transported, but then it will be less. The magnitude of transport will be much less here because very small ions are moving. But if it is bound to a mineral colloid, as it is shown here, then it will be the transport range will be much larger. So it will go to a longer distance, or it can get bound to bulk mineral phase, which is actually shown here. So in the bulk mineral phase, directly the neptunium may be binding, or it may be binding as a function, as a complex of this mineral colloid. So either way, you will find that it is the neptunium becomes now immobilized because it is bound to the bulk mineral phase. Now the mobile neptunium is which is going as such transported as the ion, or it is getting transported as the complex formed in the mineral colloid. Now this binding, this can be by ion exchange, where the actinide ion can get exchanged with an ion present in the mineral surface. This is called the ion exchange, or it can be by something called a surface complexation. So that mechanism of the surface complexation I will be discussing in one of the subsequent slides. So this surface complexation can take place on the surface of iron, manganese, aluminum, titanium, or silicon oxides, which have this hydroxide, carbonates, or the sulfides at the clay edges. So these type of things can be, this surface complexation can take place. Now the actinide mineral interaction. So you have this mineral surface as shown here. The schematic is given here. It can have, depending on the pH value, see here, if the increasing pH value, mineral surface can have a zero charge at the pZc, and if it is lower than the pZc, it will have a positive charge, and at the higher than the pZc, it will have a negative charge. So this is how the mineral surface will be behaving as a function of the pH, and there can be interaction between the actinide and the clay oxide surface, which is electrostatic, or it can be a chemical interaction. Based on that, the complexes will be formed. If you have the anionic species, then they will be interacting at the lower pH value, or at the positive species will be binding. The mineral surface at the positive part of the mineral surface will be binding the negatively charged complexes, or at the higher pH value where you have the mineral surface having a net negative charge, it will be binding with the positively charged ions or the complexes. Now for sorption or retention, they should have opposite charges, that is the mineral surface and the binding actinide ions should have the opposite charges, and if you want to be released or the dissolved from the mineral surface, then you should have the same charge species. In that case, it will be released from the mineral surface. Now the mechanism and the nature of the complex formation. As I have already mentioned, this is a two types of interactions. One is ion exchange, where the interlayer cation in the clays, which is getting replaced by the cations, the actinides. And also there can be surface complexation with the surface hydroxyl group. So in this case, it is binding with the hydroxyl groups present at the mineral surface. And the nature of the complex can be either inner sphere or outer sphere. In case of inner sphere, there will be either partial or no hydrogen sphere of this metal ion when it is forming a complex. For example, we have shown here some complex. This bigger one is the metal ion, and it is having some water molecules are present. Now this will be moving actually. Now when it is going to bind with this clay mineral, in that case these water molecules which are there around the metal ion, those water molecules are to be removed, and then it will be forming a complex. In case of the outer sphere complexation, the water molecules need not be removed, and there can be interaction between the water molecule which is binding to the metal ion with that of the clay mineral surface. So that is how it is forming an outer sphere complex. And in this case, one where we have shown inner sphere complex, where all the water molecules are removed from the inner coordination sphere of the metal ion, and that is how it is forming a complex with the clay minerals. If one wants to have the finer details of the mechanism, then the following can be considered. Now, we also have outer sphere substance, inner sphere surface complexation. So there are some of the examples I have shown here. In case of the outer sphere substance, we have this. This is the aquated complex of the actinide. Actinide is symbolized as ANX plus, and there are Y number of water molecules forming a hydrated or the aquated complex of the actinide ion. Now this entire thing is coming, this entire species is coming very close to the surface, and then it is forming outer sphere substance. So that is how it is interacting with the negatively charged part, and then it is binding in the surface. And also there can be inner sphere surface complexation. In this case, you have this actinide H2O-Y, the same species, whatever I have mentioned here. And in this case, the same species is now interacting with the surface species, which is shown here. Along with that, it is forming some bonding. That is how it is the inner sphere surface complexation. That can be actinide colloid attachment. In this case, you have this colloid, means this actinide is binding with the colloids, where the colloid can be either intrinsic colloid or pseudocolloid. That can be surface precipitation. In this case, this actinide ion is interacting with hydroxide, and it is forming a precipitate. As you know, this hydrolysis, it can form the species like OHX species will be formed, and this will be forming a precipitate, and it will be lying on the surface. There can be surface induced redox reaction also, where this oxidation state can go change from X plus to X minus 1. The reduction is taking place, and there also can be co-precipitation or solid solution formation, where you have this actinide ion which is interacting with a mineral surface, and it is forming a actinide mineral co-precipitation or the solid solution formation. So these are the different types of interactions with the actinides are forming with the clay mineral at the mineral surface. But as I've already mentioned, it can form subson, it can form surface complexation, it can have precipitation, or it can have co-precipitation, but there can be also reduction in the surface. Now these can be monitored by spectroscopic techniques, those are the EXAPS or the TRLFS, and also other techniques such as Raman as well as Fourier transfer infrared spectroscopy. Now we'll take some example. Uranium-6 uptake we would like to study by goethite and kaolinite. So in this case, what we do is we should try to understand the PCSN diagram of that of the uranyl ion. Now, as I have already mentioned, with the actinide chemistry course, this uranyl ion also forms very strong complexes with carbonate as well as also with the hydroxides. So if in the case where you do not have any carbonate present in the system, so you have the species uranyl ion at the very low pH values, and which actually goes on decreasing, and as you form the monohydroxy species, and subsequently you have the dihydroxy species also, and like that you will have different polymeric species also are formed. This is how the speciation of uranyl ion with increasing pH values it shows. But if you have the carbonate present in the aquatic system, then you have these carbonate complexes are formed. So at the low pH value, you have the uranyl species as already mentioned, and you also have the carbonate species formed at around pH 5.5 or so. So you have this uranyl carbonate species which at a higher concentration of the OH minus or at higher pH values, you get the uranyl carbonate species which have more number of carbonates are attached. Or you also can have the polymeric, or in this case you have the dimeric species where you have the hydroxo as well as carbonatous complexes are formed with the two moieties of uranyl ion. So now let us see whether we have the studies carried out at different pH values containing carbonate as well as without the carbonate. Now this example, we come here for this uranyl ion uptake by goethite as well as kaolinite. At pH7, we have both goethite and kaolinite have positive charge, which is determined from their pZc value. So before pH 7 and negative charge, it can be after pH 7. So now we'll see, we mark here at the pH 7 is the value we mark here. We will see before pH 7 and after pH 7. Now carbonate free goethite, if you take, that is the red line, which are the experimental values, we see that. So there will be, initially there will be no absorption of uranyl ion, but subsequently with increasing pH values, then there will be uptake of this uranyl ion because of the hydroxy species, and definitely it will increase and it will be going up. Even after pH 7, you get nearly 100% uptake of the uranyl ion. Now you go to goethite, where the carbon dioxide is there, shown by the blue line in the figure. In that case, initially, of course, we have this uptake is there, but beyond pH 7, because of the carbonate complexation, so it is forming now the negatively charged species, so it starts dropping. So it is not forming a complex in that case, because after the pZc values, there will be repulsive interactions, so it is not forming any complex. Now if you have the kaolinite in air, in that case also similar behavior is observed. Like goethite, initially you have uptake starting from at pH 4 values and it is going up to pH 7, and then there is a relatively more steep decrease in the uptake of uranium. That means uranium is coming out of kaolinite phase. So now what we see, this is a very simplistic case we have seen, in which case we had only carbonate present, but actual conditions, groundwater conditions, you have the humic acid also present in the aquatic system. That is, the humic acid will be present and it forms complexes with the trivalent lanthanides or actinide ions. Here, for the convenience, we have taken the trivalent lanthanides, which is behaving more or less similar way as that of the trivalent actinides. So we have taken the europium as the case study, and we are trying to see how it is, substance is there onto the alumina surface, or whatever is aluminum hydroxide surface, how this uptake of this europium 3 ion is there. So we have 3 case studies. Number 1 is just aluminum hydroxide suspension we have, and we try to study the europium substance onto that. And for the case B, we have the aluminum hydroxide suspension with dissolved humic acid, and case C, where you have the suspension of aluminum hydroxide and humic acid hybrid. So both humic acid also in the suspension, as well as aluminum hydroxide also is there in the suspension in case of C. Now we come to the first case A, where you have only aluminum hydroxide suspension. As shown in this figure, this europium 3 will be forming a complex with aluminum hydroxide at the pH value which is greater than the pZc value. Now this is the black points are representative of this case A. So you see here that initially this uptake is not there, or the substance is not there, but beyond pH 5 there is a slow increase in this uptake, and then you find this some sort of a saturation is reaching beyond around pH 7.5 or so. It is because of the complexation of europium 3 ion with the deprotonated aluminum hydroxide, which is there beyond pH 7.5. So this is what is our case A. Now coming to the case B, here we have the humic acid in the solution phase, as shown in this case of the figure. You have the humic acid also in the solution phase. That is how now it is forming a complex. It can form complex in the 2 ways. First, europium humic acids complex is formed, and that whole complex is present in the solution phase. Then europium without forming a complex with the humic acid, the chance is very, very less, but definitely some fraction of the europium 3 is not forming a complex with the humic acid, and that particular fraction of the europium 3 plus ion is binding to the aluminum hydroxide surface. The third case is the europium 3 is forming a complex with the humic acid, and the humic acid is binding to the aluminum hydroxide surface. So in this case, in the last 2 cases, that is the europium 3, which is binding to aluminum hydroxide, or europium 3 humic acid complex, which is binding to the aluminum hydroxide. In this case, europium 3 is getting immobilized on the alumina surface. On the other hand, the europium 3 humic acid surface, it is actually mobile. It is present in the solution phase and it is mobile. Now, in case of this case C, we have this aluminum and humic acid both are fixed. That means the humic acid is now interacting with the alumina surface and it is a part of this alumina. Now in this case, europium 3 is forming a complex directly with alumina as shown here, or it is binding to the humic acid, which is in turn is already fixed with the alumina surface. This case is represented by the profile given by the red balls as the data points. Now we also come to the thermodynamic modeling of the surface data. As I was mentioning, it is something called the surface complexation modeling. So here we have the different surface reactions. For simplicity, surface hydroxides are represented as SOH. So in case of the silicates, we have this type of functional groups are there at the surface with the siloxyl groups which are having triple bond SOH. Now this can take up a proton and give this type of group where it forms a cationic surface site, or it can also release a proton and giving a anionic surface site. So that means this silica is behaving either way. It can have a cationic site, also it can have an anionic site, and these metal complexation reactions can be either with the cationic site, also it can be with the anionic site, depending on the nature of the complex the metal ion has formed. The complexation reaction also can be there directly binding to the SOH functional group which is there present in the silica surface, where you have this Mn plus metal ion which is binding to the SOH, again where this sort of a replacement reaction, where this hydrogen ion is coming out of the silica surface. And similar way, you also can have the hydroxy complex of the hydrolyzed species also interacting with the SOH surface, and there also you have one hydrogen ion is coming out. So now this is how the surface complexation is taking place in the silica surface. Now when we have different type of clay minerals present in the aquatic system, they will be forming similar type of complexes, and the surface complexation model of SCM, which is actually a chemical model, but it takes into account this complexation which is taking part with the metal ion, or in this case the actinide ion with different clay minerals. It takes care of this molecular description of the substance. It also has an equilibrium approach, and it is analogous to the complex formation in the solution, but it has to take care of the mass balance, charge balance, as well as the equilibrium constant. So how to go about it? We have the equilibrium constants. The K values as mentioned in the above reaction with the metal ion, this Km or the KMOH values are already reported for a particular clay mineral, for a particular metal ion in the literature. So we can try to have our experiments done, and after getting the experimental data, we can try to fit into the different type of complexation, the clay minerals, and then from that we can get an idea what is the mechanism of this complex formation or the substance, the clay mineral. I have given one case study here in the right hand side figure, where actually the neptunium substance onto different clay minerals has been done here. In this case, we have taken bentonite clay, and this uptake has been seen at two different ionic strength conditions, that is 0.01 molar as well as 1 molar conditions given by the black and the red data points. And this modeling has been reported in the literature. This blue line is actually that of the montmorillonite, which is reported by Tachi et al. And this purple one is the again the uptake value of neptunium, which you can calculate from the equilibrium constants, which is reported by Bradbury and Baynes. This is for again montmorillonite. And this black line which is given here, this is reported by Polar et al. And this is for gaethite. Now gaethite apparently is playing a more important role in case of the bentonite clay, whatever has been taken in this particular study. And it's as you can see, this fitting curve, whatever is obtained considering the gathite, which is matching very well with the experimental data points, suggesting that gathite is probably playing a more important role in case of the absorption of this neptunium ion into this bentonite clay. This is how the surface complexation model, actually this is helping. And there are two approaches in this surface complexation model, that is the component additive or the CA model, which I have already discussed, where you have the different type of clay mineral and you take the log K value from the literature and then you try to do it, give the weightage to those fraction of the clay mineral and try to generate, model the data and match with the experimental data. And the second approach is the generalized composite or the GC, where you have the surface data and you keep on doing the iterative fitting, and that is how you can find out what are the composition, what are the mechanism of the absorption of the actinides onto the clay mineral. Now, the colloidal transport of the actinides, there are two types of actinide colloids which are identified in the groundwater. As already we know that actinides, when you go to very high pH values, they undergo hydrolysis and they also form the polymers under the existing conditions. So those cases you get actually more than one number of actinide ions, they come together and they form colloids. So that is called as the increasing colloid or the real colloid, or some people call it also eigen or primary colloid, or even true colloids. So these are basically the actinide hydrolysis products that through the oxo or hydroxy bridge formation. There is another one is called a pseudocolloid. There actually the colloid is formed by another metal ion, and in that case this actinide is sorbed onto the colloids formed by the second metal ion. That can be some other metal ion like the transition element metal ion, which is forming a colloid under the groundwater condition or the experimental conditions, and there the actinide is getting sorbed onto the colloid of the other metal ion, and this is called a associative or pseudocolloid. Now, what are the factors which are determining the stability of the colloidal system? Now, the factors of this colloidal system mainly depends on the electric charge on the surface of the colloid. Naturally, depending on the charge, if the charge is too much, the colloid will break. Then because of the repulsion between the colloid particles, and it will prevent them from coagulating and settling out of the solution phase. Also, the factor which is determining the pH value at which the colloids have the zero surface charge, that is the pH, PZC. Then the farther the pH of the colloidal system from the PZC, the larger is the surface charge and the more stable is the colloidal system. Each colloidal system is characterized by its pH, PZC, so that the pH can be adjusted to stabilize or destabilize it. Also, the factors which are important is the salt effect or the ionic strength on the surface charge. So depending on that, if the electrolyte is present in a colloidal solution, the cations tend to adhere on a negatively charged colloid to compensate the excess local charge of opposite sign, and vice versa for the anions. This will reduce the double layer potential of the colloid and enhance the coagulation process in that colloidal system. Now, formation of the colloids and their studies. They have already mentioned this formation of the eigen colloids. This is the eigen colloid or the true colloid or the intrinsic colloid. In this case, the hydrolysis is the primary step, which is leading to the polymerization and thus generation of the actinide colloids. And the tendency of this formation of the actinide colloid, of course, it depends on the charge, the ionic potential of the actinides. That is the tetravalent actinide ion has a higher chance of forming a intrinsic colloid. And also the actinide hydroxide and oxides usually have a very small solubility in the natural water, so making them the common source of the intrinsic colloid. In case of the pseudocolloids, their attachment of the actinides on the groundwater colloid, which are already present in the groundwater system, which result from various geochemical processes, and also it can be also from the weathering of the rocks and minerals. You have some colloids are present in the groundwater system, which will be basically the platform where these actinides will be getting absorbed, and for subsequently they will be migrating in the groundwater system. Now the formation of the colloids and their studies, the methods for the study of actinide colloids, the properties that are of interest for the environmental point of view, and the colloid size distribution can be done by studies like our DLS or so. Then also this charge on the colloid can be found out by the pH and the optical actinide uptake by the colloids can be done by the normal uptake studies. By ultracentrifugation, by filtration or ultrafiltration, this can be done to separate the colloids from the dispersed media. Electrophoresis or zeta potential can be done to determine the colloidal charge, and adsorption studies can be done the normal way by adding a radio tracer into the solution phase and then to find out how much the radio tracer is going onto the colloids or the exchanger, or in this case the clay mineral, and that is how from the adsorption studies can be found out. The particle size of colloids are determined using DLS or the dynamic light scattering method. Also scanning electron microscopy or energy dispersive X-ray spectroscopy or transmission electron microscopy. These are the techniques which can be used to get the size. And as mentioned here, you can find that these jobbed contaminants, this is the phase, is the water phase is there, and this is the sediment phase which is shown here. And you see that this rock or the sediment phase is shown here. Now these are the contaminants, the dissolved contaminants, which are the actinides. So they are normally mobile in the water surface, but they can get jobbed also onto this rock surface, which is the immobile surface. This is how they can get immobilized onto the sediment or the rock. They can also form intrinsic colloid, or they can form a complex with the pseudocolloid, and then also they will be in the mobile in the water surface, and they can get moving in this way, and that is how this actinide can get transported. So this is how this is a two-phase method I have shown, and this is the contaminant transport in a three-phase system, where mainly the transportation is done by either by intrinsic colloid formation or resorption onto a pseudocolloid. Now to summarize, actinide clay interaction, you have this solid, like here you have iron oxide or iron hydroxide, which is present here. Taken for example, it is true for any other oxide, rock or clay materials, and which can have the radionuclide, which is having the water molecules here, which is coming here and it is binding to the iron oxide. This is called the subsum, and can be desorption can be there, where you have the radionuclide is forming a complex. You can have a complexation with the ligand, that is how it forms a complex that is coming out of the jobbed clay mineral. This is a desorption. It is determined on the pH value and the complexation constants. Once it is forming, it can have the dissolution also. Then it will come again to the aquatic medium. There can be co-precipitation and there can be dissolution. That is how this complex also, in the presence of ligand, there can be dissolution from the clay mineral. That is how this becomes mobile. And finally, it comes to the colloidal surface. This is a colloidal surface is given. So this is basically, it says a pseudocolloid, where you have the radionuclide, which is forming 1, 2, 3, 4 of them coming together and forming a complex block of species, which can facilitate the transport of actinides. And this is the pseudocolloid, where you have this another metal ion is forming the colloid, and the radionuclide is binding with this, and this is how it is embedded onto the pseudocolloid. So this is how the colloidal system it is migrating in the groundwater system. That is the reason for this actinide migration behavior in the environment. So we have completed the actinide chemistry and the actinides in the environment. The next two lectures will be on the transactinides.